the context, the sort of topic area that I'm working on for this project is part of reinforcement learning. And reinforcement learning is a learning paradigm that enables practitioners to specify decision-making behaviors to computers. So some notable successes of this that you may have seen are, say, in AlphaGo, which is a computer agent that learns how to play Go by thinking about where to put the next stones. Humanoid locomotion, so say in robotics, when you want to figure out how to control a humanoid robot to walk around in different environments, and also recently how to control, say, a nuclear reactor, a nuclear fusion reactor at nuclear tokamak. And the underlying sort of shared concept behind all of this is that of reinforcement learning, wherein what you do is you want to reward good behaviors and punish bad behaviors. And what my project is about is it's about some work on simulated robotic control. And the problem that I'm trying to solve is how do we have an agent that learns how to produce motor torques from position and velocity sensor information. So I'm going to present some results in these domains. The sort of high-level summary of what I'm going to present is a new algorithm. It's called DoubleGum. And I'm really excited by this algorithm because I think it bridges the gap between the theory that we have of reinforcement learning and also what we do in practice. And we also present a really efficient, effective algorithm that's really simple to implement as well, that solves a variety of these simulated robotics tasks. So to begin with, I'll just introduce reinforcement learning. And while I'm sure a lot of you are familiar with reinforcement learning, I just thought I'd go over this just to introduce some notation that I'll be using into the rest of the presentation. So RL is really about the problem of trying to get an agent to behave in an environment. So here we have like this sort of reacher agent, and it's moving around in this environment, and it's trying to get to this ball over here. And what the agent does is that at every time step, so at time step t, it produces an action A using a neural network pi that is essentially some probability distribution over all the different actions it could take. And the agent samples an action that it then uses to control the environment. What happens in the environment is that the environment is governed by this transition function, which is in the most general case, probabilistic, but it doesn't have to be probabilistic. And what happens is that the environment is essentially controlled by the action, and the transition essentially determines how the environment will evolve from one time step t to the next time step t+1, and using this transition probability p. Also, the other thing that the environment has is a reward function, which tells you the amount of reward that the agent would receive between two consecutive time steps, so between that states st and st+1. And essentially, what we're trying to do in reinforcement learning is we're trying to create algorithms that maximize this quantity called return, which is g. And g is something that takes in a sequence of state and action pairs. And it's this discounted sum of all the rewards. So I didn't specify it here, but this gamma here is meant to be between 0 and 1. And this makes sure that the rewards, the sum of rewards from beginning to end is finite. Because if you have like an infinite number of time steps, then this reward becomes infinity. So this discount factor essentially enables you to ensure that the sum of rewards are bound. And so the onus on the reinforcement learning agent is to try and behave in such a way to learn a policy pi that produces actions that maximizes quantity g. And the sort of onus on the practitioner is to design rewards that enables the agent to learn behaviors that you wanted to learn. For instance, say in this example, we want the agent to touch this red object that keeps on moving around. And so we want to maybe have a reward function that tells us about the distance between, say, the end effector of this robot and the ball at any time step. In this talk, though, I'm not going to talk about reward design. Instead, I'm actually just going to talk about the algorithms. So I'm going to talk about how the agent learns this policy pi to produce these actions that leads to these rewarding behaviors. So a neat way that you can specify this whole, the objective of this algorithm is in the language of probability theory. So we have this quantity G, which I introduced in the previous slide, which is the quantity that you want to maximize. And because the environment in its most general form is probabilistic, what you want to do is just want to find a policy that ensures that on average, over all the different paths that you could take in the environment, this return quantity is maximized. So here I've defined the probability of like the sequence of state and actions by this sort of Markov chain looking thing that looks like a Markov chain. So here you have the transition probability P between like different states. Then you have the policy pi, which tells you about the probability of taking an action given a state. And here I have the reward as defined. Sorry, the return as defined here is the discounted sum of rewards. The central quantity that we have in reinforcement learning is something called a Q function. So it's so named because it measures the quality of taking the action A in this current state, ST. And usually it's written with a superscript pi to indicate that this is the Q function of policy pi, because this expectation here is taken with respect to P subscript pi, because it's a probability induced by a particular policy. And what this definition tells you is that this is the Q function for a particular state and action pair at time step t. And it tells you what is the expected return from this current time step until some point in the future, n time steps. And there's a really nice property of the Q function that I'm now going to derive. And that property is that of self-consistency. So to derive this, first, what I'm going to do is I'm going to decompose this probability into the, I'm going to use the Markovian nature of this definition here. I'm going to substitute it into this expectation. So I can decompose this expectation into 3 operators. And then the next step I can do is I can rewrite this return as well in a sort of recursive format, because it's the discounted sum of returns. So what I can do is I can take the first return and then write the return of all the subsequent time steps from the next time step t plus 1. And I can rewrite this return as such. And then I can notice that these expectations can be rewritten. These expectations are independent of R, rather than R is independent of these expectations. So I can move these expectations into this term of expanded. And then I can notice that this term here, this expectation in this G, is actually just the definition of the Q function, but it's just one time step into the future. So this is the definition of the Q function at time step t. This is the definition of the Q function at time step t plus 1. So effectively, there's a really nice property of the Q function in which that it's sort of self-consistent with itself. So say the Q function at time t is related to the Q function at time t plus 1 by this equation. So what I'll do in the rest of the presentation is, for sort of neatness of notation, I'm not going to use the subscripts t and t plus 1. I'm just going to have s and s prime instead, because it will make just notation a lot easier. And also, we can also note that this Q function holds for any pi that we can we choose. It can also hold for the optimal policy, which we call pi star, in which case the Q function we can rewrite as Q star, in other words, the optimal Q function. And there's this really nice property that we can also use as well, which is to say that when we have the optimal policy, we can rewrite this expectation by just taking the maximum A that maximizes the optimal Q function at the next time step. And that's because the optimal policy, there's a nice mathematical property that I won't have time to go into proving now. There's a really nice mathematical property that tells you that the optimal policy is always determined by taking the action that maximizes the Q function. And so I didn't have time to go through the proof, but the sketch of the proof is that of induction. So the base case is that of taking the last time step and noting that here the Q function is just going to be a single return. And then if you just want to maximize the Q function, i.e. behave optimally. So to maximize the Q function, you just take the action that just maximizes that. And then you can have an inductive step, which says, okay, suppose I am at, say, a future time step. If I want to act optimally in a future time step, then this tells me how I should act. This tells me how the optimal Q function relates to the Q function future time step. And so you can say that if I act optimally by taking the max future time step, I'll have to do that the current time step. What you want to do in deep Q-learning is you want to learn a Q function that learns or tries to approximate the optimal Q function. And that's because when you've learned the optimal Q function, that tells you how to act optimally, as I've explained in the previous slide. So we take this equation, which is called the Bellman optimality equation, because it corresponds to the optimal, the Q function corresponds to the optimal policy. And then what we typically do in deep RL is that we learn a Q function that essentially satisfies this equation. In other words, we want the Q function to be consistent with itself with respect to this equation. And the way that works is that typically we take a Q function and then we just pass it through, we just make the substitution of Q star for Q theta, and then we form this into a loss by essentially minimizing the discrepancy with the left-hand side and the right-hand side to ensure that the Q function is consistent with itself. And if we use a squared loss, that typically implies that in deep learning, that typically implies that you have normal noise. And then what you're actually doing is you're actually doing maximum likelihood estimation of the parameters theta with respect to this normal noise. But the problem is that if you plot the errors that you get in this equation, so if you think about the left-hand side and the right-hand side, and if you plot the errors of the left-hand side minus the right-hand side, if you look at the histogram of those errors, that doesn't follow this normal distribution, which is really the assumption that you have behind the squared error. So the focus of my project is to basically say that, okay, so maybe we're using an inaccurate noise model currently for Q-learning. So how can we come up with a new, more accurate noise model? And then how can we use that noise model to produce a better algorithm? And does a more accurate noise model lead to better performance? The spoiler is yes, and that's what I'm going to talk about in the rest of the presentation. And there's going to be two parts of this. The first part, I'm going to derive a new noise model that better fits the histogram of the TD errors. And in the second part of the derivation, I'm going to convert that noise model into an algorithm that we can use. So the way that I'm going to derive the noise model is via the following 4 steps. So if we want a neural network Q with parameters theta to learn the optimal Q value Q star, what we really want is an objective that relates the two of them together. But that's very difficult because we don't have access to the ground truth values of Q star. So what we do is we use our friend, the Bellman optimality equation, and we can just substitute the an expression for Q star based on the Bellman equation and say, okay, well, maybe we can compute these targets and learn a neural network against these targets. But then the problem still persists because we still don't know what the optimal Q function, Q star, is. And here's sort of where the problem occurs. When we approximate Q star here with Q theta, in other words, we're essentially doing a bootstrapping estimate because we're using the current value Q theta to estimate Q star by essentially this step of the development operator. We're introducing some sort of noise because we're trying to approximate Q star with Q theta. And so the loss function that we use has to account for this noise, and that's why I've written L1 here. So these are 3 steps so far, but in reality, some deep RL algorithms are even more complex. So in the introduction section, I said that one strategy you could use is to learn a neural network Q theta that is consistent with respect to the development equation by minimizing this equation. But there are other deep RL algorithms, such as this DDPG, deep deterministic policy gradient algorithm, that uses 2 neural networks. And those neural networks are called a critic, which learns a Q function, and an actor. And what the actor does is that it is another neural network, pi, with parameters phi, that tries to maximize the Q function. And essentially, this learns to approximate this max operator over here. And so instead of taking the max over all A primes here, you can just use the policy pi here as that approximation of the action that maximizes the Q function. And this is quite useful in domains where maybe you have a very, very large action space, or you have a combinatorial action space where it's not trivial to compute this maximum. And so you can approximate that with this function. So that means if we use this actor, we actually introduce yet another noise source. And so again, we have to have a loss function L2, which accounts for this other noise source that we're introducing. So what the derivation I'm going to present in the next slides will be about is how do we quantify the noise introduced by the bootstrapping approximation and the actor approximation? How can we essentially relate L2 to L1 and back to L to have a loss function that relates Q theta to Q star? So these are the 4 steps that I'm going to take. And let's begin with the objective. So we begin with this following this following assumption, which is what gives the Double Gumbel Q-Learning paper its name. So here we assume that there are 2 Gumbel noise sources, G, and it's a very particular, specific, and you could argue perhaps a contrived formulation of how the noise source looks like. So here we have G, which depends, which is sampled every time you have new parameters and every time you have a new action. And then here you have another Gumbel noise source, which doesn't depend, which doesn't change on every new action you sample, but only on the parameters. And also G is state dependent, so therefore it's heteroscedastic. In other words, it depends on the state. And the way that we've written that is that we have a Gumbel distribution with location 0 and spread beta, which depends on the state. So for those of you who aren't familiar with the Gumbel distribution, it looks something like this. It's a unimodal distribution and it's skewed. So this is the general shape of the distribution. This is a screenshot from Wikipedia, who I thank dearly for the screenshot. And the interesting property of the Gumbel distribution is that it arises from something called the extreme value theorem. So say if you have any distribution of noise, Z, and you have, say, number of samples, and if you take the sample that has the maximum value, the distribution of the value of this maximum value follows a Gumbel distribution. So there was a question about like the interpretation of earlier about the interpretation of like noise and Q functions, and my sort of answer at this point, which I'll build on, is that in 1993 there was a paper by Frohn Schwarz, and they presented some empirical evidence that showed that there was this noise model behind Q-learning. So in other words, if you think about the optimal Q function Q star, and this is your neural network Q theta, what's happening is that at every time you have a new set of parameters, a state and action, your Q is going to be a noisy approximation of your optimal Q function Q star, and is related by some arbitrary noise distribution. Now, the authors of that paper didn't really quantify what that distribution was, but they had some evidence to show that there was some noise. And really, our contribution to show is to argue that this noise term is comprised of these two heteroscedastic Gumbel noise sources. So yeah, I know what you're all thinking. You're thinking, like, why on earth is he talking about these two Gumbel noise sources? Like, where does that come from? Why is he really doing that? And the reason why is because we want to get an analytic solution for what's happening when we approximate this Q star here with Q theta. And so if we substitute this expression here, if we rearrange this expression for Q theta, and we substitute this in for the next states S prime and A prime, what happens is that this is the only, these two Gumbel noise sources is the only way that we can take this max operator with the Q theta and some noise term that is analytically tractable. So if you have any other noise term here that is added to like S prime, and you take the maximum over that, you will get a Gumbel distribution as per the extreme value theorem that I said in the previous slide. But the problem is that you can't relate the location and spread of the resultant Gumbel to the distribution that you put into the maximum. And really, these two Gumbel noise sources is the only distribution that lets you compute something analytically tractable after the maximization. So let's have a look at how that looks. So let's take this max operator. And then what we're going to do is we're going to just sort of note that this Gumbel noise source here is because it's independent of A, we can take this out of the maximization and just think about the first two terms. And then we can use this identity, which is to say that if you have the maximum of a Gumbel random variable plus a shift, the location, the resultant distribution is a Gumbel distribution shifted by this operator here, which is the log sum x of this shift, divided by the beta here, which is dependent on the state, which is the spread of the original Gumbel distribution that you're putting in. And the reason why that we have a second Gumbel on the outside is such that these two cancel each other out, such that we can have a very nice just equation, essentially a non-noisy equation for this maximum operator by rewriting this expression. And then now if we want to think about how we can introduce the actor, there's also another identity that we can use, which is that we can decompose this log sum x operator into the sum of two terms, which is an expectation term and a cross-entropy term between the probabilistic policy pi and also another distribution p theta, which is given by the Boltzmann distribution here, where z is normalizing constant. So now if we think about just substituting this entire expression back into this expression in the bootstrapping term here, then essentially that gives us this following noise model, which is the one that I'm going to use in the rest of this talk. So as a sort of brief summary, what I've presented in the previous slides was the derivation of this noise model. So in other words, is that in Q-Learning, we have two noise sources, and they're both heteroscedastic Gumbels, G theta A and G theta. And these are sampled from the Gumbel distribution. And in the right-hand side of the Gumbel equation, to account to the fact that we have, by taking the maximum, we also have this additional term we need to take care of, which is a cross-entropy between the policy and this P, which is this Boltzmann distribution. And what we can do is that we can simplify this for first the left-hand side. We can actually make use of a really nice identity, which is that the difference of two Gumbel distributions from the same distribution is actually that of a logistic distribution. And because these two distributions are heteroscedastic or state-dependent, the logistic distribution we end up with is also state dependent. And on the right-hand side, the problem with computing this cross-entropy term C is that it's kind of intractable when your action dimension A becomes large or when it becomes combinatorial. So what we do in practice is that we represent here C as a scalar hyperparameter, which we determine at the beginning of training. And we just fix that to a fixed value throughout training and just hold that constant throughout training. So if we assume the left-hand side, substituting the left-hand side and the right-hand side of the original noise model, what we end up with is this equation. And this is only an approximate equality. It's an approximation because here we've approximated the cross-entropy C by this hyperparameter. And this sort of approximate noise model that we end up with this logistic noise it presents us an algorithm that has really two key characteristics. The first is that we have the scalar hyperparameter, which is determined, like I said, at the beginning of training, and that's fixed. And the second is that we can learn beta and also Q by the generalized method of moments by matching a Gaussian with this logistic distribution. So the matching works by essentially making note that for a logistic distribution with location 0 and spread beta, that has the same moments as a normal distribution with location 0, with mean 0, and with the standard deviation given by beta multiplied by this constant. And then if we do essentially maximum likelihood estimation of the to learn the moments of the normal with the to learn like the standard deviation and mean here by Q theta, then that enables us to learn what the value of beta should be. And then we can use that beta here in the right-hand side to multiply it by C to compute this target. Oh yes, and in this loss function here, I've rewritten this right-hand side, this red box, as this term y, just for ease of notation, because otherwise this equation will go off the screen. The way we do that in practice is that we have a Q function that has two heads. It's got a Q head and it's got a beta head. So another thing, I guess, another approximation here is to note that here the betas only take in are only a function of S, but because we have a Q function that has inputs of both S and A, now we have a beta that also depends on S and A, and so we're having neural network of Q and beta, and by minimizing this loss function, we can learn both via this method called moment matching. So the really interesting thing about essentially, I think, all of what I've presented is that surprisingly, this loss function, this noise model fits that of the empirical data. So here, as a reminder, this is the original graph, and this TD error here is formed by subtracting the right-hand side of this equation from this Q value and plotting the histogram of that. And as a reminder, say the typical assumption that you have with the normal distribution doesn't fit the, so I see someone has raised their hand, but I'll just finish explaining the slide for answering. And it doesn't really fit the histogram of errors. Whereas in the noise model that I presented here, there's a better fit between, say, the histogram of the differences between Q and the right-hand side, and this logistic distribution that I fitted to it. And finally, so the C graph here shows how the goodness of fit of these two distributions varies throughout training. And this is a negative log likelihood. So the lower it is, the better the fit is. And it shows that essentially the noise model that we propose is a better fit throughout training of these errors. So the main result of this paper is that, so I evaluated the algorithm DoubleGum on 4 simulated robotic suites, and they're given by sort of the GIFs here. So we have the DeepMind Control suite, which tells you about how to do locomotion of these simulated robots. So here we have an acrobot, which tries to swing up. Here we have a hopper, which tries to hop forwards. We've got another similar suite called MuJoCo, which again measures the locomotion ability of agents. So here we have an ant trying to go forwards. We have a humanoid here trying to walk forwards. We have the MetaWorld suite, which is about how to manipulate objects in an environment. So here we've got the task of trying to insert this peg into this drawer. And here we have a task of trying to close this rather small window. And then finally, we have another locomotion suite, which is more challenging perhaps than the DeepMind Control and the MuJoCo environments, because the terrain here is uneven and it's always varying between episodes as well. And we're trying to control this bipedal walker to try and traverse this terrain from one end to the other. So the algorithm that we have, DoubleGum, is based on benchmarked against 3 different algorithms. So we have the DDPG algorithm that I've referred to in previous slides. And this differs from DoubleGum in the sense that it doesn't have heteroscedastic logistic noise in its noise model. It has homoscedastic normal noise in the noise model. And it doesn't have the beta term in computing the targets. There's also TD3, which is a modification of DDPG. And the way it modifies DDPG is by training an ensemble of networks. So here it has 2 Q networks subscripted by I. And the way it computes its target is by taking the minimum value per sample of the Q target network. So essentially, you can think about this as behaving somewhat similarly to the way that this beta multiplied by C works. So earlier I said that the interpretation of this is akin to that of optimism or pessimism. So say if C is negative, then what you're doing is you're actually subtracting away the uncertainty in the return from the targets. And this is essentially decreasing the magnitude of the targets. So in other words, you're having pessimistic targets. And you can think about TD3 as essentially doing the same thing as that, but using an ensemble. And the reason why they did this in their original paper was because they found it empirically worked better, but they didn't really have any theoretical justifications for why that was the case. And then there's also the popular algorithm soft actor critic, or SAC. And this is similar to DDPG and TD3 in a sense that it uses a normal noise, which results in the squared error loss. And it has a different target to the 3 by actually just taking into account the entropy of the policy pi. And in my paper in the appendix, I show that how this is actually yet another way of approximating this beta multiplied by the cross entropy. So what I've done to evaluate, first of all, is I fixed the C hyperparameter to minus 0.1, which was a value that I found worked well across all tasks. And across these 4 suites, we benchmarked on 33 tasks with this fixed hyperparameter. And what we found was, in general, in aggregate, over all these 33 tasks, we performed better than the 3 baselines. So this metric here is an interquartile mean. It's a method of aggregating the performance over, say, all these 33 tasks. And here is sort of like the aggregate learning curve of how our agent, of like the rewards that our agent gets over time versus the number of time steps it's been trained on. So this is like the aggregate over the 33 tasks in the 4 suites. And in below, what you see in these 4 graphs is that I've split up the aggregation into an aggregation per suite instead of aggregating across all tasks over all 4 suites. Here I've just aggregated the suite over all tasks per suite. And what we see is that in sort of for each of these algorithms that are in the baseline, there is usually like a suite that the algorithm doesn't perform well in. So say DDPG doesn't perform very well in MuJoCo, but it performs really well in DeepMind Control and MetaWorld. soft actor critic performs really well in MuJoCo, but it doesn't perform very well in DeepMind Control. And TD3 sort of performs equally well on all 4 tasks, but not to the same extent that DoubleGum does, as shown by the aggregate performance over all 33 tasks. So another thing that I then looked at was what happens if we vary the hyperparameter. And if we vary the hyperparameter C, what basically happens is that, well, unsurprisingly, the performance changes. But the general trend is that you want C to be negative, but not too much. So the best performing hyperparameter C was that of minus 0.1, which is this orange line over here. And if C was more negative, if it was minus 0.5, performance was lower. And similarly, if C was 0 or positive, the performance was likewise lower. And you see this trend sort of repeating in the other 4 environments as well. So say for DeepMind Control, if C was very negative, i.e. the minus 0.5, it didn't have very good performance, but setting C to less negative values helped. In MuJoCo, the best performing value was minus 0.5 over here. And in MetaWorld, you have different performance values of C, but the general trend is that you want to be a little bit negative. And here's sort of where the connection to pessimism and optimism comes in, is that so what I did here was I just plotted the right-hand side of this equation here with varying C's, and I wanted to see how that changed on individual environments. So what you can see is across these environments is that when C is large, the magnitude of this, not really the magnitude, the sort of the value of this right-hand side here is larger. So that's why I decided to call the C hyperparameter the pessimism factor, because it essentially controls how optimistic or pessimistic, how large or small your right-hand side is. And so I've sort of hinted at this, I think, previously in the presentation, but what I then wanted to do was I wanted to then compare performance of DoubleGum, where I adjusted the pessimism per suite C against all the other algorithms. So what I did was I then compared against, say, an algorithm that was the best of DDPG and TD3. So that is basically you adjust the hyperparameter whether you use twin networks or not in DDPG or TD3 suite. Then I also did I had another baseline where you adjusted whether or not you did twin networks or not, whether or not you had twin networks on SAC as well. And then I also had another baseline, which is called finer TD3, which is when you, instead of having just 2 networks and taking the minimum of them, you have instead 5 networks, and then you take the ith the jth smallest value. Instead of just taking the smallest out of 2, you have the jth out of 5, and this enables you a more fine-grained control of pessimism rather than just minimum of 2. And again, what we show is that in aggregate, our algorithm DoubleGum has more efficient learning performance compared to the 3 baselines. And the reason why I think this is the case is because we're fitting the distribution, logistic distribution, logistic noise distribution, the TD errors better, and also as a result of fitting beta and subtracting it from, or adjusting that from the target, that enables us to have a more accurate estimation of the optimism or pessimism compared to the other methods. And also, it's a more fine-grained method of adjusting pessimism and optimism than having an ensemble, because having an ensemble will give you like a discrete hyperparameter, whereas C is a scalar hyperparameter, so it's continuous, so that it gets you a finer method of controlling the pessimism. So that's really the conclusion of what I want to present today. So what I want to present was a new algorithm, DoubleGum, which I believe is simple to implement. It's also efficient in learning, and it's also quite effective in learning good behaviors as well. The key takeaway is that I've hopefully tried to convince you that noise in deep Q-learning is shaped by these two heteroscedastic Gumbel distributions, and that when you account these distributions in a new algorithm, yields, to the best of my knowledge, I think, state-of-the-art aggregate performance over these 33 continuous control environments. And also the training behavior of this algorithm is quite stable across the 32 environments, as shown by the aggregate graphs. So please feel free to email me with any questions. So also feel free to ask questions to me now as well. At the end of the presentation, I'll stick around if anyone has any questions. But just in case you have some questions after the presentation, I'm very happy to take emails. Code is over here. So if you want to run this algorithm, test it out in your environments, it's all on GitHub. And please let me know, actually, if you do test it out, let me know how it performs. I think, yeah, I'll just conclude by saying, thanks to my co-supervisors, Aaron Bovier and Pierre-Luc Bacon, and also the wider Mila community for, which is where I did most of the research. And I've really enjoyed my time there. And yeah, so that's it. Thanks for listening. And I'll stop here.